Welcome to today's video on fields. This is the third part in our series, and today we're going to look at point forces. And specifically, we're going to look at the force between two objects, whether they be two masses or two charges. Okay, and we're going to look at the inverse square law. So how the distance between the two objects, you can see that red object and the blue object in the middle, how that differs with the distance between them. Okay, let's get started here. And we're going to have a look at two masses. So the first mass, big M, here on the left, and we're going to have a look at a smaller mass here on the right, little m. And they're going to be separated by a distance of r. And our question is, what happens as we increase the distance r? So, how does the force between the two masses change with r? Okay, let's go to our diagram here created on Geogebra. So looking at this, we've got a red mass that goes outward and a blue big mass in the middle, and the red mass goes out with a greater distance r. And I'm going to create a field strength that is related here by this lime green mass moving out. The lime green sphere increases in surface area by a factor of r squared, as you can see there, that area increasing. This actually then means the field has to be distributed across a bigger area. So the red dot, which is the little m, has a weaker and weaker field. Now that red dot, which is the red point mass, in relation to the green field, decreases by a factor of 1 on r squared. So that actually means here we get our rule or relationship, which says that the force between the blue and the red mass decreases by a factor of 1 on r squared. So this can be used with an analogy, much like how a balloon gets thinner and thinner by the same factor as it gets blown up. Okay, let's now look at the laws that govern gravitational forces and electrostatic forces. Now, these are the two really big rules that we're going to learn in fields. The first is the law between masses, which is Newton's universal law of gravitation. Newton came up with this in the 17th century, and its force equals G, which is a constant, times the two masses, m and little m, on r squared. Now, G is just a constant of proportionality. It's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And this force always acts between two masses, and this explains all the planetary motion that we know, the gravitation here on Earth and that kind of thing. It's pretty amazing he came up with this. Now let's go to electrostatics, which is Coulomb's law. And Coulomb's law here states that the force equals K, big Q, little q on r squared. So the force equals a constant K, which is 9 times 10 to the 9 Newton meters squared per Coulomb squared, times the charges between them divided by r squared. So here we go, Newton meters squared per Coulomb squared. Now, this force acts on the two masses, between the two charges. Okay, and I guess the only difference here with electrostatics is that the direction might be dependent on whether they're like charges or opposite charges. Like charges will repel each other, and opposite charges will attract, and so the force direction is dependent accordingly. Okay, as we can see here, this diagram just explains this formula: the big M in the middle, the little m out in space, and that r is the separation between them. Similarly with the charges, big Q, little q, and the distance between them there. Okay, fun fact time. Who's in for this? I'm not sure you can understand the gravity of this fun fact, but a teaspoon of neutron star weighs 5.5 billion tons, which is a ridiculous amount of mass. Okay, for this final question, example question, we're going to understand what happens in terms of using this Newton's law of universal gravitation, and find out what the force is on 1 kilo mass at the surface of the Earth and also at low Earth orbit, 300 kilometers above. As you can see here, I've started a diagram. We've got 1 kilo at a distance r of the Earth and 1 kilo at a distance re, or radius of the Earth, plus 300 kilometers. We've got the little m, which is the 1 kilos, and we've got the big M, which is the mass of the Earth. So using this formula of F equals gmm on r squared, we know from calculations previously that the mass of the Earth is 5.97 times 10 to the 24 kilos. We know that G from previous is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. The little mass is just 1, so 1 kilo. The radius of the Earth is 6,371 kilometers. Changing that to meters, we always need to work in meters, is 6.371 times 10 to the 6 meters. Now, at the surface of the Earth, so using that radius r, we can plug that all in our calculator. So we have F equals 6.67 times 10 to the minus 11 times the mass of the Earth, shown there, 5.97 times 10 to the 24, times the mass, the 1 kilo mass that is on the surface, divided by that radius of the Earth in meters squared. Okay, now chuck that all in your calculator and you get bingo, 9.81 newtons. Now that looks very familiar, doesn't it? Kind of like that acceleration due to gravity value that you're aware of. Okay, so really interesting answer there. Now let's look at 300 meters high. Okay, all that changes is the radius is 300 kilometers higher. So that's 300,000 meters. So we add 300,000 meters and we get 6,671 kilometers, or 6.671 times 10 to the 6 meters. We put that there in our same form as what we had before, so gm little m on r squared, and we get a different answer. So we get 8.95 newtons, which is a little bit smaller. So the gravity 300 kilometers out is a little bit weaker. So if we go up in altitude by around 4.5%, it actually means our force goes down by 9%. That's my dog in the background. Cool. Thanks for watching today's video. As always, please subscribe. It's much appreciated as always. And continue to click. Next video is on field strength, which I'm sure you'll enjoy. And definitely leave some comments and feedback as always. Thank you guys.